All right, everyone. So we have chapter 5, which is on more application of Newton laws. Right. So one force that we talked about in the previous chapter, but didn't really go into a great detail, was the friction force. So we just said that, all right, so if there's an object and this object basically is in contact with the surface, remember, so the surface gives us two forces. Basically, surface is an agent, always exert two forces on object. One is a perpendicular to the surface force, which is basically the normal force. The other one is always parallel to the surface. So it's either going to be to the left or going to be to the right. So basically, always parallel to the surface. So we call it friction. So F for basically, lowercase f for friction. Okay. Again, so this is, you can see that this is due to interaction between object and its environment, mostly, let's say, the surface. So basically the surface of the object, the bottom surface of the object, or the top of the, let's say, ground or floor or whatever it is. And that interaction is basically what we call force of friction. And friction, again, is an opposing force. So that's why I have, either to the right or to the left, because that force basically doesn't have specific direction. Normal force kind of does. It's always perpendicular, on the object, right? Perpendicular to the surface. But friction can be to the left or to the right, depending in which direction the object is being pushed or pulled. All right. So now, there are two types of frictional forces. Okay. One is known as a static. Okay. The other one is known as kinetic. So, I mean, both of them are let's say types of friction forces. Now, the reason we have two types of friction forces, because technically then the surface, when it exerts force, it can exert force when the object is at rest. That means imagine object is at rest, and then, let's say, imagine that it's being pushed to the right. So let's say some force is pushing to the right, some applied force. Well, friction right away starts opposing by applying force to the left. And for a while, for example, friction force can, cancel out, can basically resist being pushed or pulled. And while the object is being pushed or pulled, but still, remains at rest, we're dealing with the static friction. Okay? And static friction is what prevents objects from moving when you apply liberal force. You can try right now, if you have some kind of desk in front of you, just give it a little push. You will see, right? The desk is not moving at all. Why? Because of friction. Because you are applying force. If there was no friction, it would have been just accelerating up, forward in the direction you're pushing. But because there is a friction, and friction basically depends on the weight of the object, right? Heavier object, greater the friction. So you have a hard time pushing right now. Even if you push harder and harder, your desk most likely will not move. Again, because of the friction. If there was no friction, you do the same experiment, you go and push the same desk on ice, it will just start accelerating no matter how light you're pushing. All right, so the force of static friction, again, static friction is basically when you're applying force on the object, but object still remains at rest, is always greater than this kinetic friction. And kinetic friction is when, let's say, you push and push and push, and eventually you make the object move. Well, when the object starts moving, the friction doesn't just disappear. It's still there. But actually, you're dealing with the kinetic friction as soon as the object starts moving. That means the object basically has this, period, or let's say when it's being pushed and it's able to resist by the friction, static friction force. But static friction force, we're going to see that it has a maximum value. And once you overcome that maximum resistance it can give you, then the object starts moving, and then you're dealing with the kinetic friction. And kinetic friction always less than static friction. So static friction always greater, because it's much harder to push something that is already at rest. That means when something is at rest, it's much harder to push it and make it move than pushing something that is already moving. Since friction is also from surface, just like the normal force, they are actually related. Friction force is proportional to the normal force. And then that proportionality sign or proportionality constant is what we call coefficient of friction. So this coefficient of friction, which is mu, so then any type of friction is equals to coefficient of friction times normal force. And obviously what we have, if it's a static friction, then it's a static coefficient. If it's kinetic friction, then it's a kinetic coefficient. And kinetic and static coefficient for even the same surface-surface interaction is actually different. So that's why one of the things we have here is this. The kinetic friction is always less because coefficient of kinetic friction is always smaller than coefficient of static friction even for the same surface. If you're looking at this kinetic friction, which is coefficient times normal force, this is more or less always remains constant. Let's say if it's 10 newtons, it's always going to be 10 newtons. Coefficient of static friction is actually adjustable. So that can depend on how much the object is being pushed or pulled. And it can adjust itself to try to match. So we're going to see that in a little bit, but you can say that a static friction force is adjustable. That means it's a variable. It can be zero. It can be up to its maximum value, right? But kinetic friction is pretty much constant. Once you calculate some kind of value for that, it remains constant. So you can say, right, direction of the friction force is opposite direction of the motion and parallel to the surface in contact. And coefficient of friction is merely independent of the area of contact. So that's why you can have like a tiny object or like a big box or something like that. You're still getting the same friction. So that's why we can generalize it. And we can say, object doesn't matter. We can represent it as a particle. And because the area, surface area, right, the contact area is independent of how much friction, it is experiencing. So let's kind of, see what we have. Static friction, again, acts to keep the object from moving. That means when you're pushing, for example, here's what we have. Imagine, you have a, object sitting there, okay, like a trash can over there, right? Well, even if nobody's pushing or pulling in a horizontal direction, you already have the normal force and weight, okay? So those two forces, one from Earth, another one from surface in the vertical direction, is already acting on the object, but they cancel each other, so object's sitting there at rest. If you start to push the object to the right with some applied force F, then if the surface is rough, that means it can exert some kind of force compatible to the applied force, then the force will be in the opposite direction of the applied force. Now, one thing we can do here is this. We can calculate this maximum static frictional force. So maximum static frictional force, and it is equals to coefficient of static friction times normal force, okay? So this equation can allow us to find what is the maximum amount of resistance the surface can give you. So let's say we get 20 newtons. Well, it means that it can go as high as 20 newtons, but cannot go beyond 20 newtons. So imagine you apply force of 5 newtons. Well, it gives you negative 5 newtons. You do 15 newtons, it gives you negative 15 newtons. Why? Because it adjusts itself. All right? So and always try to match whatever the applied force is, because it's goal to keep the object at rest in equilibrium, in static equilibrium. If there's an applied force of 15, it doesn't go all the way to its maximum value 20, because it means that opposing force is greater than applied force. Your system then accelerates to the left. Makes no sense. So then it can match. For example, you do 20 newtons. Okay. So let's say you do 20 newtons. And it does 20 newtons. Okay. So you do 20 newtons. Now it goes negative 20 newtons. All right, so what do we get here? Well, we're already getting the, up to this maximum. So you can see, right, this graph very nicely demonstrates that. So when there is no applied force, there is no, friction force. It makes no sense, right? You cannot have a friction force when there is no applied force. Because imagine if you have an object and, suddenly there's a friction force out of nowhere, pushing accelerating the object left or right. If no applied force, friction zero. That's why, let's say you have a vertical axis as a, static friction or the, friction, and the horizontal axis is applied force. So when it's zero applied force, friction is zero. As you increase the applied force, friction increases. It matches 1-to-1 applied force until you get its maximum value. let's say 20 is its maximum value. Once you apply 20 newtons, right, you already feeling that object starts slowly, already starts sliding. Anything above that, because you can see right over here, anything above that, let's say even 20.5 or like let's say 21, then you are pushing strong enough that it starts sliding. Right away, then the friction opposing becomes kinetic instead of static. As soon as it starts moving, then you are dealing with kinetic. And you can see, right, static friction compared to kinetic friction is always less. So that's why, you have this constant, more or less, kinetic friction acting on the object during its motion. It doesn't adjust itself or something like that. It basically gets one value and continues basically acting on the object. All right, so friction force arises from the nature of two surfaces. Because of their roughness, contact is made only at the few locations where peaks of the material touch. So the friction forces arises because one peak physically blocks the motion of the peak from the opposite surface. That means, in a way, even if we can say that, okay, the smooth surfaces and things like that, there are always imperfections. If you go to a microscopic level, you will see some, bumps and peaks, something like that. So, and they always, let's say, when you're sliding, right, they're, in contact with each other, and that's basically what you get, the friction from, pretty much. And also from chemical bonding, which is basically the atoms of the box attracted to the atoms of the surface. And when you're pushing, you also have to overcome that, let's say, molecular bond between those atoms and molecules. All right, so then let's look at, several examples. Okay, so remember, again, what we're doing here is assuming that, the surface now is not, frictionless, because, in chapter 4, we kind of looked at a few examples where we said the surface frictionless, which means that we could ignore the friction as a force. But generally, let's say if you're told that it's frictionless, and if you're told it's smooth, only during those times you can ignore the friction. But generally, you can imagine that friction is always some part of the system, and if it's small enough, we can neglect it. But generally, it's not small enough. In real life situation, you always have to take into account friction, only maybe in vacuum when there is no friction. All right, so a block of wood is pulled at constant velocity by a horizontal stream across a horizontal surface with a force of 20 newtons. The coefficient of coefficient of the kinetic friction between the surfaces is 0.3. And the force of friction is, so basically we want to calculate the force of friction. Also remember, one thing I want to mention here is this. When we have this equation, friction equals coefficient times normal force. So remember, on the left side is the force of friction, units of newtons. On the right side is a normal force, units of newtons. So then you can see, right, the quantity that we call coefficient of friction cannot be any other units, because you already have newtons and newtons. Anything else, it will basically, change it. So that's why mu is a unitless quantity, and generally, as I mentioned in the lecture, right, it's between 0 and 1, where the number closer to 0 means a smoother surface, number closer to 1 means a rougher surface. Right. So here's the free body diagram for this, for this system, for this problem. You have a block of wood being pulled by a tension force of 20 newtons, and we are given there is a coefficient of kinetic friction. That means we have to assume there is a kinetic friction, and obviously there is a normal force, which we can also put like F of n, right, and gravitational force. Basically, just slightly different notation, but same thing. Now, if I put it in a table, then I have, in terms of looking at my horizontal and vertical forces, right? So I have then tension, friction, normal force, and weight. Let's say, put it like that. All right, so this is plus T, this is 0, this is minus F, and it's a kinetic, we know that. So this is 0, this is 0, this is plus N, this is 0, this is minus mg, and here net force. Now, since it is being, moving, like, let's say in a horizontal, let's say in a horizontal surface, right? So technically this is 0 in a y direction. And the question is that, how about this, net force in x direction? Well, here where you have to be careful, where you have to be, reading the question very carefully, because it says it's being pulled by some tension, but it is moving at constant velocity. Constant velocity means that there is no acceleration. Net force is 0. All right. Then I take that and I can say, all right, so then T minus F of K equals 0, right? And then equation 2, then N minus mg equals 0. So N is balancing mg, T is balancing F of K. And since T is 20 newtons, that means F of K here is in 20 newtons as well. That means you can still have equilibrium when you have a kinetic friction, but this equilibrium has to be dynamic equilibrium, not kinetic. That's not static. Static equilibrium only when you have a static, friction. But you can have, let's say, dynamic equilibrium with, kinetic friction, which just means it's moving with constant velocity. All right, so let's look at another example. By the way, there was another way I could have, solved for the normal force, so for static friction, for kinetic friction, if I did like, let's say, mu k times normal force. But in this particular example, I could see that normal force equals mg. But see, I was not given the mass of the block. So this way, solving the f of k would have been wrong, or not wrong, but like, let's say, impossible, because I don't have the mass of the block. So I can't really solve it using this equation. All right, so here's another one. A block of mass m is pulled at a constant velocity across the horizontal surface by a string as shown. Okay. The magnitude of the friction force is, again, we want to find what is the magnitude of friction force. All right, so similar example, but this time it's basically being pulled to the left by a tension that it's at an angle. But still, what we do here is we approach the same way. That was a free body diagram, let's say, already given to us. So we look at x component, y component, right? And let's say what I have here is my tension. Here's my friction. Here's my normal force. Here's my weight. And this is net force. Okay. So that means, again, I have 4 forces acting on it. And again, I have a constant velocity. It means right away I know it's 0, 0. The only thing here is this. The tension here is basically to the left, right? Technically, it's in, it will be pretty much making the object, go to the left. But it's in equilibrium, so it doesn't matter which one I take positive, which one I take negative. So I'm going to take, again, to the right as positive, and up positive. So this is the negative t cosine theta, and then this is plus t sine of theta, components of the tension. Then this will be plus f, 0, friction acting to the right, f of k. I can, indicate that. Normal force acting in a positive y direction, and weight acting in a negative y direction. So then my equation 1 would be negative t cosine theta plus f of k equals 0. So then f of k is equals, right, t cosine theta. And then equation 2, I have plus t sine of theta plus n minus mg equals 0. Okay. Now, what I have here is this. Then normal force is equals to mg minus t sine of theta. All right. So then technically, those are the things I can do from here. Because, I have one way that I can look at in terms of what is f of k. Another way, f of k would have been mu k times normal force. And basically, this is then mu k times mg minus t sine of theta. So 2 ways we could, look at f of k. Obviously, if you're given tension and theta, let's say, would have been easiest to use the equation 1. But you could use the other one as well. All right, so this problem is mostly sort of like, let's say, finding the expression of it. All right, so then let's look at another one over here. A 100-kilogram crate rests on a thick pile carpet. A weary worker then pushes on the crate with a horizontal force of 500 Newton. The coefficient of static and kinetic friction between the crate and the carpet are 0.6 and 0.4 respectively. Notice that static friction for the same surface is always higher. Find the subsequent friction force exerted by the carpet on the crate. Again, we're asking to find the static friction. Here's then what we have. Again, we're given free body diagram. where you have an object with four forces acting on it. So this is, putting everything, organizing in a table. All right, so we have applied force, we have friction, we have normal force, and we have weight. And here's a net force. And if I look at, then this is plus F, 0, minus F of, minus F, 0, 0, plus N, 0, minus mg. I know that this is definitely 0, but here it's not clear. Okay, so we know that mass is 100 kilogram, all right? And I know that in y direction, everything is 0. So like, let's say if I get equation 1, then this is F, applied force minus friction equals to mass times acceleration. But the question is that, are we in equilibrium in x direction or not? We don't know that yet, because I don't know if it's a kinetic friction or static friction. See, we're given both. Equation 2, though, tells me that n minus mg equals 0, so n equals to mg. This is, what we have. And technically, I can even calculate, because it's 100 kilograms times 9.8, so it's 980 newtons. I know this for sure. It means it's 980 newtons. Well, the question here is this then. How do I know if I'm dealing with static friction or if I'm dealing with kinetic friction? Because I know that my applied force is 500 newtons. The question is that, is this higher than maximum static frictional force or not? So that means if the maximum friction force is less than 500, that means it's, we're dealing with, that means this is strong enough that the box will be pulled, the crate will be pulled. So obviously, what we're going to try to do here is then we can calculate maximum, static frictional force, which is coefficient of static friction times normal force. And I have that, right? I have coefficient of static friction, which is 0.6, and I have normal force, which is 980 newtons, and I can calculate this to be 589 newtons. All right. Okay, so that means maximum static friction is 589 newtons. Now, what does it mean about the applied force? Well, if applied force is 500, then friction can go as high as 589, so it has no problem, pushing back with 500 Newton, right, to, keep the system at rest. That means my friction is a static friction, and it's 500 Newtons when it is being pushed by 500 Newtons to the right. And then it's resisted by 500 Newtons to the left, okay? All right, so here's one more example. A black beam rests on a surface for which the static and kinetic coefficients are 0.6 and 0.4 respectively. Again, same thing. And what we do here, we say that, okay, the ropes are massless. So what is the maximum mass of block A for which the system is in equilibrium? Okay. Now, remember, we kind of looked at similar things in the previous chapter, but let's say if there was no friction on the surface where the B is, then A will go down, B will accelerate to the right, and the system will be accelerating. But in this case, what I have here is there's a gravity acting, so this is MAG acting on box A, so it's pulling it down. But, and there's a tension, right? Let's say TA. And then B has then TB acting on it, okay? But there is now also a friction. There's a friction, static friction, acting on block B, right, to keep it from accelerating. All right. So this is then what we have system in equilibrium. And the question is that, if this is 20 kilogram, what should be the value of mass of A? What should it be so that the system is not accelerating, but indeed is in equilibrium? Because if A is too heavy, then it can actually, overcome the static frictional force. Because remember, this MA, if it's pulling down very hard, then technically then tension can try to, the rope will stretch a little bit and apply more tension, then this TB will then increase, and then it can maybe overcome static frictional force. Okay. Now, again, the best way to approach this is to take this problem and break it down into two parts. So break it down into two parts. So I'm going to take this to be my system B, this be my system A. And then remember, so this is interacting system, which means that I can always assume acceleration of 1 is equals to acceleration 2 if there is one, right? And because we are told that ropes are massless, that means if things like this, if this is 0, that means the other one is also 0. If ropes are massless, that means TA is also equals TB. So, and we are given that, right? Okay. Now, if I look at, mass A, what I have here is this. So this is the, free body diagram for A. Mass A has two forces acting on it. So let's say I can say MAG or thing like this. I can just say weight of A and then tension, up. Again, because I say TA equals TB, I can just say it's T. All right, so if I put it in a coordinate system, right, I can say, right, so here's my, forces in the table, put in a table. So here's tension, here's weight for A. I can ignore X for this one, just say it in terms of Y. And again, because it's not accelerating, I can just take any direction positive. So I take up positive, so plus T minus weight of A, net force gives me 0. Then this is equation 1 for that, where T equals weight of A. That means equals to MA times G. Tension equals MA times G. Now, same way, then I look at system B. For system B, then I say, okay, here's my, free body diagram. System B here is at the center, and the forces that acting on it will be tension to the right, and then friction to the left, and it's a static friction, normal force up, and weight of B down. Okay. So then let me make a table for that. Forces, X components, Y components. Let's see, I have T, friction, static, normal force, and weight of B. Okay. So here's my net force. I want to have, static equilibrium, right? So plus T, 0, minus F of S, 0, 0, N, and 0 minus MBG, right? So weight of B here is MBG. Then I can use that to get two more equations. So equation 2 will be T minus F of S equals 0, which means technically then, T is equals to F of S, right? So since T minus F of S equals 0, that means T is equals to F of S. Okay. And then equation 2, then I have normal force minus MBG equals 0, so normal force equals MBG. Okay. Now, what I'm going to do here is that I'm going to then combine all of those things together. Okay, I'm going to combine them. I'm going to say, all right, so equation 2 tells me tension equals MA times G. Sorry, equation 1. I do have two equations. Equation 2 tells me then tension also equals to F of S. That means MAG is equals to F of S. But we also know that F of S equals mu S times normal force. But then equation 3 tells me that normal force equals weight of block B, so MBG. That means MAG equals mu S times normal force, which is then MBG. And then from here, all I have to do is this. I can see that I can cancel G from both sides. Remember, our goal was to find A. Then MA is equals to mu S times MB. Well, mu S was 0.6, MB was 20 kilograms. That means what we get here is 12 kilograms. There you go. That means mass of A has to be no more than 20 kilograms for the system to be in equilibrium. Anything greater than that, then the system will accelerate, accelerate down. That means mass of A will be heavy enough to accelerate down. Tension will be strong enough to overcome static friction, and you will be, accelerating system rather than having a, system that basically sitting there in equilibrium at rest. All right, so here's a tough one. So this is basically, you can think of like as hard as you can see in this type of problems. So you have two blocks. So a block of mass M1, which is 250 gram. By the way, ignore the, this 100 kilogram that it says over there. So the writing is kind of like wrong, but same. Just ignore that, that part. So, but the setup is exactly the same. So you have a mass of, M1, which is 250 gram, is at rest on a plane that makes angle of 30 degrees. That means this is 30 degrees with the horizontal. The coefficient of kinetic friction between the block and the plane is 0.1. So rather, smooth surface though. The block is attached to a second block of mass M2 equals 200 gram that hangs freely by a string that passes over frictionless massless pulley. When the second block has fallen 30 centimeters, what will be its speed? All right, so in this problem, you get kind of two hints that the system is accelerating because you're only given the kinetic friction, right? So, which means that the object will be moving, okay? And if it's moving right now, so it can be moving at constant speed, but, we can generally assume that in this type of problems, you either have an object that is, at rest, or if it's accelerating. If it's not accelerating but moving, you will be explicitly told that it's moving at constant velocity. Otherwise, it's going to be very vague. So here we're going to assume that, it is accelerating because remember, so technically, if it starts from rest, then it's going to be accelerating, and we want to know as this guy, let's say, has fallen 30 centimeters, maybe somewhere over there, right? So let's say when we get to somewhere over here, how fast it's moving. Okay, that means we're given that it's kind of more or less going down by delta y of, negative 0.3, right? So negative 0.3 meters, or we can take that down to be positive direction. We can also do that. But let's say the delta y here is 0.3 meters. We will actually take down as negative, as positive for this particular problem. All right, so let's see what we have. We are given mass 1 and mass 2, right? So let's say given. So we're given that mass of 1 is 0.25 kilograms. I guess I need more room. And mass of 2 is 0.2 kilograms. We're also given that V1 initial equals V2 initial equals 0. We can assume that, they start from rest. Also, we are told that there's a coefficient of kinetic friction of 0.1, theta equals 30 degrees, right? And then delta y is 0.3 meters. Okay. Now, it's not a free fall. Mass, let's say 2, which is here, doesn't go down in a free fall, right? So we need to then use dynamics and everything, right, to get that. So now we need to find speed of 2, right? Final speed of 2. Okay. And let me tell you this, it's also going to be same speed as the 1 final. It means they're both going to have the same speed because they have the same acceleration. Remember, A1 equals A2 because both of them are connected by the same, by the same rope. And also the tension for 1 and the tension for 2 also going to be the same because, again, same rope. But we can't right now, we don't know how to find speed directly, right? So with given information. Okay, so we have initial speed, we have displacement, and in a way, I need either, either time, acceleration, right? Or let's say, either time or acceleration in order to find the speed. Okay, so that's what we're going to do. So there's no way for us to find the time, but we can find acceleration using Newtonian dynamics. And the way we do that is very similar to what we did in chapter 4. Again, take this to be my system 1, this to be my system 2, and then combine them to solve for the acceleration. Remember, I showed you last time, right? So basically you have mass 1, mass 2, tension, and acceleration. So you have those 4 variables that you deal with whenever you have a interacting object like that, right? Two objects connected by a rope and they're moving. So remember what I said, that if I give you two out of those four, you can calculate the other two. And I am, right? I'm giving mass 1 and mass 2. That means you can set it up and easily calculate acceleration. So technically, we don't really need tension at this point. So we can eliminate and just solve for acceleration. All right, so that's what we're going to be then doing. Okay, it's just this is a little bit more complicated because there are more forces involved. All right, so let's then do that. Let's look at system 1. So system 1, then this. Okay, so it is, put it like that, right? So system 1 is, object on an incline. Okay. So I'm going to take my coordinate system like this. This is y-axis. This is the x-axis, because the one going to be accelerating upward, and 2 is going to be speeding up downward. So that means if I take my object 1 to be at the somewhere in the middle of the incline, right, it's going to be then speeding upward. Okay. So then what are my forces acting on this object? Well, forces are two forces, right, in x direction, and that's tension and friction. Okay. And it's a kinetic. So those are two directly in the x direction. But then I also have a normal force up and gravity down. So this is basically f of g1. Remember, this ends up being the same angle theta. So then when I'm looking at the force table for this, so let's see, I have tension, I have static friction, kinetic friction, sorry. I have normal force, and I have weight. So this is, and with like weight of 1. Okay. So here's my net force. Okay, so let's look at tension. Well, tension is in the positive x direction. There's no y component. Friction, negative x direction, no y component. Normal force is up, no x component. And now weight. Well, for weight, I have this, right? So I have m1g sine of theta for the x component, because remember, x component will be this guy over here. And then m1g cosine of theta for the y component. Since I'm taking up positive, this is first quadrant, second quadrant, third quadrant. I think I have one extra over there. And then this is fourth quadrant. That means gravity acting in the third quadrant, so negative, negative. There's no acceleration in the y direction, but then there's an acceleration for the object 1, right, block 1, in a x direction. That means what I get here is this. Okay. Equation 1 will be tension minus kinetic friction, then minus m1g sine theta equals m1 times a. Okay, so right, so basically tension is pulling against kinetic friction and the component of the gravity. And it's strong enough that basically overcoming those two. Equation 2 then will be normal force minus mg cosine theta equals 0. All right, so those are my two equations, let's say, for now. So then let's do this. Let's go to then system 2. All right, so system 2 is a little bit easier. So I'm going to take down to me my positive y direction. And let's say if this is my object, right? So then I have two forces acting on it. I have weight of 2, and then tension up. Okay. And force table. So 0, 0 for the x. So I have tension and then weight 2. But in a y direction, then what I can say here is this. Negative tension, positive weight 2, and then positive m2a, because it's accelerating down. No, this one was accelerating up. That means from here I get then equation 3, which will be m2g, which is weight 2, minus tension equals m2a. All right, so I get those two equations right now. Okay then, what I need to do here is find acceleration. Remember, right? I need to find acceleration. And I use the equations where there's acceleration. It's 1 and 3. So I put it here, so it's 1. So t minus f of k minus m1g sine of theta equals m1a. And equation 2, m2g minus t equals m2a. And I add them together. Because if I add them together, I am eliminating tension, right? Add those two together, you eliminate tension. And my, resultant equation then becomes m2g minus f of k minus m1g sine theta equals, then becomes m1 plus m2 times a, right? Because m1a plus m2a, I can factor out a. All right. And then technically from here, I can just basically solve for a because I have everything that I need. Okay. But let's say one thing I have here is that there's f of k over there. But remember, I know that f of k equals coefficient of k times normal force. That means I can then say, all right, so acceleration equals 2. And I have this giant equation. So I have then m2g minus, so now f of k, I'm going to put mu k times normal force. But equation 2 then tells me what normal force is, right? Normal force is mg cosine theta. Because n minus mg cosine theta equals 0. That means n is equals to mg cosine theta. So it becomes m2g minus mu k, then mg cosine theta for normal force, then minus m1g sine of theta, that's for the gravity component, right? Perpendicular to the parallel to the surface. Then this is divided by m1 plus m2, which is mass 1 plus mass 2. And that's my equation. All right, so it's you can see, right, it's relatively complicated compared to what we've done before. But you see, it requires m1, m2, and then if you go back and look at my given table that I started with, right? So I have m1 and m2. It needs coefficient of kinetic friction. Well, I have that too. And it has a cosine of theta and sine of theta, but only this theta, and I have that too. That means all you have to do is just plug in and calculate for whatever the acceleration is. Okay. Because the next step will be this. Okay, so I completely ran out of room, but let me do it then here, because it's technically one equation that I need from here. All I got to do from here is this. I want to find how fast I'm moving when I move down, let's say, 30 centimeters. And what I have here is this. I have my initial velocity in the table, right? Initial velocity. I have my displacement. And now I have, let's say, if I use this, I can calculate the acceleration, whatever it is. And then what I have to do here is this. Final velocity squared equals initial velocity squared plus 2 times acceleration times delta y. And that's the equation I have to use. And, I end up with, since v initial is 0, then just basically 2 times acceleration times delta y. And take the square root since, v final is squared on the other side. That means all I have to do is just use this equation. 2 times whatever I get for acceleration times displacement of 0.3, then take the square root of that, and then that's my final speed. And if I do everything correctly, we should get 0.84 meter per second. And that's my final speed for the object, that traveled, let's say 0.3 meters. Doesn't matter, let's say 0.3 meters here in this direction or 0.3 meters in that direction. Both of them actually will have the same speed because they have the same acceleration. Right, so that's why you can see, right? This is a little more complicated where you have to take your, time, break down everything, write down what is given to you. You have system 1, system 2. Your goal will be just get those 3 equations, right? Get those 3 equations. Then you can, eliminate tension. So for acceleration, which end up being this equation expression over there, right? It's complicated only because there's also friction, right? But, if you practice a little bit this type of problems, everything is then pretty much the same. Okay, same approach. Free body diagram, force table, then equation. Free body diagram, force table, then equation, right? And then put them all together and organize them.